In the last segment, we talked about how we keep liquids as liquids. And the fundamental thing is that we have to keep our particles together through what we call intermolecular attractions. And it begins with determining what would keep them together, and one obvious way to do that is through polarity. So I gave you a few examples on drawing Lewis structure and then its shape according to Vesper, and then going back to your electronegativity chart to determine your polarity. Now segment 3 begins here. What happens when you take these individual molecules, for example, and instead of just having one of them, you have two of them and you bring them close together? Well, one thing that can happen in its most basic sense is something that we call a VanderWaals force. And one type of VanderWaals force is called a London dispersion force, which occurs due to electrons moving. So let's say, for example, you have a nucleus, okay, and I'm just going to draw a nucleus like this. And we have our electrons just going around and around and around and around and around. Okay, now we know they don't really work quite that way, but in its simplest form, we're just going to say that. So let's say we say stop, and our electron is right there. So for that femtosecond in time, this atom here is partially negative on this side and partially positive on that side. Now let's say I take another atom of that same molecule or atom or whatever it is that I have, and that electron moving, 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 except now instead of stopping over here, I'm going to stop, actually, you know what, I'm going to stop him over here. Okay? Partial negative, partial positive. Okay? So what ends up happening is as the electrons are moving around, we get a slight induced dipole. Induced dipole. Due to the electrons that are circulating in the substance itself. So any molecule or atom with an electron will do this. Okay? But as you can imagine, this is very, very weak. London dispersion forces are very, very, very weak because as that electron is moving, it's moving very, very quickly. And so this induced dipole is incredibly, incredibly weak. Okay? Page 10. Your dipole-dipole forces are due to permanent dipoles in both substances. Okay, so for example, if I have CO2, okay, now CO2 is a little bit of a difficult substance, but I'm going to use that as an example. Okay, so here's my Lewis structure of CO2. It's linear, partial negative, partial positive, partial negative. And then I'm going to take another CO2 and I'm going to bring it close in the vicinity. This has a permanent dipole because of the polarity of the carbon-oxygen bond. Well, I'm going to have a dipole-dipole interaction right here. And so that is a dipole-dipole force between that CO2 molecule and that CO2 molecule. Okay? Now the third type is what we call a hydrogen bond. And the hydrogen bond is a bit of a misnomer. It's not a bond at all. It's an attraction. Okay? It's an attraction, but a very, very important one. And it's an attraction between a partial positive hydrogen and a partial negative neighbor. Okay? So for example, let's go back to our water. Partial negative, partial positive, partial positive. partial negative, partial positive, partial positive. So if I take this water molecule and I put it close to this water molecule, I'm going to have a partial positive hydrogen and I'm going to attract to a partial negative neighbor. So not only is this a dipole-dipole force, but it's a special type of dipole-dipole force called a hydrogen bond. And this one, you can see I'm putting lots of stars by it. This one is the most significant of the three and is most important in terms of biological substances, because most biological substances that we're interested in have to interact with water in order to be living. Okay? So what we're going to want to do is we're going to want to look at different molecules and look at the types of intermolecular forces that they have and see if we can figure out something about the way they interact. So think about this for a minute. Boiling point, the ability to go from a liquid to a gas. Okay? To go from a liquid to a gas, you've got to take those particles that are being held very tightly together as a liquid and get them to separate. So the more intermolecular forces there are, the higher the boiling point is going to be. Regarding vapor pressure, remember that the vapor pressure are the molecules that go from the liquid phase and escape into the gas phase. So if your liquid molecules are being held very tightly together, very few of them are going to escape. So if we have very high intermolecular attractions, we're going to have very low vapor pressure. Okay? We can skip viscosity because we don't really look at that too much, but the state at room temperature really is a function of these first two, and that is if they have high intermolecular forces, they are going to want to stay together as a liquid. Okay, and so they are generally liquids at room temperature, and the most important one for our purposes here is water. Okay, and because water is generally a liquid most of the time, right? Our oceans are oceans usually. They're usually not hurricanes, right? That's why we have life on this planet. Okay, now what we want to do is we want to take a few and determine which type of intermolecular attractions there are in the following. Okay, so water, we've drawn it up here. Do we have electrons moving? Yes. Therefore, we have London. Do we have a permanent dipole in water? Yes. So we're going to have dipole-dipole. Do we have a partial positive hydrogen and a partial negative neighbor? Yes. Therefore, we're going to have hydrogen bonds. So water will have all three. The ammonia. The ammonia was on the other page, and I'll just draw it again so we don't have to flip back and forth. Partial negative, partial positive, partial positive, partial positive. And let's just put it next to a neighbor so we can see this. So let's go through the three questions again. Will these have electrons moving? The answer is yes. Will there be a permanent dipole? Yes. Will there be an attraction between a partial negative and a partial positive neighbor? Yes. So water and ammonia will both have all three types. CH4. There's one. There's its neighbor. Do these have electrons that are moving? The answer is yes. All of these will have electrons that are moving. All of them. Every one will have London forces, so that's easy. However, there are no polar bonds here. So this one will not have dipole-dipole, and this one will not have hydrogen bonds. On this one, okay, I'm going to leave these other hydrogens out for clarity. Partial negative, partial positive. And I'm going to draw the second one just a little bit backwards for clarity. Partial negative, partial positive. Do we have a permanent dipole in this carbon compound? And the answer is yes. So this one's going to have dipole-dipole. Will we have an attraction between a partial positive hydrogen and a partial negative neighbor? Well, sure. We have one here. We have one there. And notice I'm drawing it with a dotted line. The dotted line shows that it's an attraction. Okay? So this one will hydrogen bond. Two more quickly and we'll be done with this segment. Okay? Okay? So partial negative, partial positive, partial positive, partial negative, partial positive, partial positive. These hydrogens here that I'm just sort of leaving small for clarity, we do not have a partial positive hydrogen anywhere. So this one here, this one does have dipole-dipole, but it does not have a hydrogen bond. Okay? And then last but not least is our CO2, which I did on the other page. Partial negative, partial positive, partial negative, partial negative, partial positive, partial negative. So dipole-dipole, but not a hydrogen bond. Again, in order to do this, you have to be able to do a Lewis structure, you have to be able to do VSEPR, and you have to know how to use your electronegativity chart. Okay? So if you do not know how to do that, or you don't remember how to do that, you're going to need how to review that. Okay? Now I will end this segment by saying this is really, really, really important. Okay? So the reason that this is important is that in order for something to be alive, it really has to be able to mix with water. Okay? And so in order to mix with water, we're going to begin our next segment on solutions.